Okay, some words of our director of the department, Profesor Carla Reyes.
¿Cómo están? Muy buenos días para todos. Reciban un saludo muy especial de parte de las directivas de la Universidad de Nariño. El señor rector no nos puede acompañar en este momento, pero en mi nombre como directora del Departamento de Física, los saludo a todos. Bienvenidos a la ciudad de San Juan de Pasto, bienvenidos a la Universidad de Nariño. Realmente para el Departamento de Física es un honor ser los anfitriones de esta 9ª versión del Encuentro Colombiano de Física de Altas Energías. Esperamos que esta semana sea muy provechosa para todos nosotros, que enriquezca nuestra experiencia como físicos, como profesores de física también. Es especial también este encuentro porque están en una universidad donde estamos celebrando los 120 años de vida institucional, fundada en 1904, junto con el Departamento de Nariño. Por eso estamos muy contentos de recibirlos, muy ansiosos que todo salga muy bien en esta semana y queremos que ustedes se lleven una muy buena mirada de esta nuestra universidad, que tiene un gran protagonismo, como lo dice el himno del departamento, desde el mar hasta el Galeras. Tenemos la universidad impactando la costa pacífica, también en la frontera con el Ecuador y también en el municipio de Túquerres. Por eso somos una gran institución que queremos que ustedes la conozcan, que ustedes vuelvan a esta universidad alguna vez para que sigamos en contacto en esta red académica tan bonita como es la física de altas energías. Entonces, expresarles nuevamente mi cordial bienvenida. Esperamos que no sea la última vez, como ya lo he expresado, y que por favor siéntanse como en su casa y como si esta ciudad de San Juan de Pasto fuera un hogar para ustedes. Entonces, muy amables, felicitaciones al Grupo de Altas Energías, en cabeza del profesor Eduardo Rojas, por haber traído este evento aquí a la ciudad de Pasto, a todo el comité organizador, tanto el externo como el comité local. Muchas gracias a nuestros monitores, que con el apoyo de ellos es posible la realización de este tipo de eventos, y ojalá ustedes los puedan estar preguntándoles todo el tiempo para que se sientan ustedes cómodos de estar aquí en la ciudad. Cualquier inquietud con ellos la pueden resolver. No es más mi saludo, muy cortico. Les deseo éxitos a todos los ponentes, que se lleven la mejor impresión tanto del evento como de la ciudad. Nos estamos viendo continuamente, estaremos por aquí para servirles. Muchas gracias y nuevamente bienvenidos.
Thank you, Professor Carla. Okay, now some very useful information about the places and please, next slide. Okay. Okay, tomorrow, see, the conference will be held in the building in front of this one, yeah? This is for tomorrow, yeah? Entonces, this is called the, how is called this building? Este edificio, ¿cómo se llama? No, el que es, sí, bloque tecnológico, ¿ya? Sí, bloque tecnológico is in front of this building. Also for the Cocha, that is on Wednesday, yeah, the buses start in front here in this. Please arrive 7:30. The buses start for the Cocha 8 p.m. It doesn't matter if you arrive 2 or 3 minutes later. At the 8 p.m. the buses go for the Cocha. Entonces, please get early this day. Okay, please, another slide, okay? Okay, there are several restaurants close. The closest one is Mr. Pollo, yeah, it's half kilometer, yeah, more or less. There are also very cheaper food in the terminal, sí, for the students, en el terminal que hay saliendo a mano izquierda, sí, sí. This is quite cheaper, and thus you can get very good food. Also, if you prefer, yeah, you can take a taxi for Unicentro. It's 5 minutes from here. See? This is for the lunch. And Unicentro, you will find in Food Square a lot of foods, different restaurants in this shopping center. Okay. please, next speak, Amelia, please pay attention. Okay. Oh, okay. Okay, this is more or less the schedule for today. Next one, the next one. Okay. Okay, that's all. Okay, please, the local organizing committee, please come here for everyone knows. See? Okay. Tonight, the Imperial, el Teatro Imperial, ¿sí? Sería Imperial Theater, ¿no? Para el Palacio Imperial, cualquier taxista, you take a taxi driver, y you ask for Palacio at 7 p.m. Yeah, listo. The price of the minimum, the minimum price for the taxi, and basically is the standard es 6,200, 6,200, okay? Entonces no se vayan, pay attention to this value, okay? Okay, if it's too long, entonces are 7,000, o sea, 7,000 pesitos, ¿sí? But don't pay more, okay? This is important information. Okay, please, the local organizing committee, please come here. El comité local organizador puede pasar para que los conozcan. And any question or any doubt, you can ask them. Yeah, they are Profesora Carla. Where is the local organizing committee? Professor Germán, listo. Profesor, the professor of the Universidad de Nariño, profesor, okay. Okay, they are a little bit shy. Okay, seems to me that's all, okay? Okay, to start with, okay, our first lecture, okay, we have Professor Chang Kee from Stony Brook University. I have to read a small resemblance of the professor. Professor Chang Kee is a distinguished professor at Stony Brook University. He wins the linear field, this is written here, prize. This is a very important prize. One of the winners is Stephen Hawking, of the winners of these awards. He is former T2K International co-sport person, okay, and leader of the United States group since 2002, worked with the former director of Fermilab, Nigel Lockyer, to establish the Dune collaboration. There are several guys here from the Dune collaboration. He's one of the most important at Dune, okay? He will talk about an overview of neutrino experiments, new results, and perspectives. Please, Professor Chang Kee.
Gracias. Buen día a todos. Me gusta esta sala, es muy bonita. Me gustaría agradecer a los organizadores por la invitación. Estoy muy feliz de estar aquí en Pasto. ¿Hay estudiantes en el público? ¿Estudiantes? Ok. So, si es así, preparé una parte de mi charla especialmente para los estudiantes. Espero que la disfruten. Okay, now I have to switch English. Okay. Fine. Let me put this one down. Okay, so my topic today is overview of neutrino experiment. But for the students, I wanted to give some introduction. So there will be how the neutrino experiment is developed. But my focus will be in the neutrino oscillation experiment, especially. We are trying to understand why universe is matter-dominated, not antimatter existence of antimatter in the universe. So that will be my theme. I will apologize for some of the other neutrino topics that is not covered in this talk. So let me start with the question, what is nothing? I don't know any of you actually thought about what is nothing. Nothing has been a tough subject of Taoism and in many ancient philosophers. This is my favorite Chinese character. It means nothing. My pen name is nothing in the heart. There's two Chinese characters, nothing in the heart. So it could be interpreted as a mindless, or but you basically empty out all the thoughts of your brain, and that becomes nothing in heart. So if you think about it physically, what is nothing? So one way we think about is that in this room, if we seal everything and put 50 meters of lead everywhere, and then pump out all the air, and it becomes vacuum. It's a vacuum. That is the closest thing that we can think about nothing. But if you wear God's glass, right, God, if you imagine you are God, if you look at vacuum, it is actually full of stuff. First thing is that if you stick your finger out, in the fingertip, there are 50 billion neutrinos passing by from the sun. You cannot stop them. And do you feel that? No? You should feel that, okay. And so there is a neutrinos, and then the vacuum is actually full of quantum fluctuation. There are particles spontaneously generated and disappear. And there's dark matter, which we don't know what it is, and dark energy, which we don't know what it is. So space is filled with everything. So what I said is that nothing actually does not exist. Okay, so think about these things. This is something for your thought. If we go outside at night and look at the sky, that the things we see is actually only 0.5% of energy budget of the universe. Neutrinos, the subject of this topic of my presentation, is another 0.5%. And then rest of all the things we know with made out of known element, that is only about 4%. And then dark matter is 26%, dark energy is 69%. So essentially, we don't know anything about universe by approximation. So universe is filled mostly with the invisibles. Neutrinos are the most abundant elementary particles in the universe other than photons. So you all know Einstein. Einstein was working hard on special relativity and general relativity and many other things. One thing he really wanted to do was unify all of the forces in nature, four forces. And so he was working on that, but he could not finish that. And then he passed away. So he said, can all forces in nature be unified in one form? So this is basically what physicists we are doing. When Newton looked at the planets going around the sun, and then looking at the apple dropping, he was able to somehow connect these two phenomena together and into gravity. That is the first known unification in physics. And then there's a Maxwell equation. That's actually the unification of electricity and magnetism. That's another unification. And then 1960s, we found out the weak theory, that is the description of the nuclear decays. And then we were able to unify QED and a weak theory, and that has become unified electroweak theory that actually resulted in Higgs mechanism. And then we have a QCD, quantum chromodynamics, that describes a strong interaction inside the proton and among the quarks. And then you have this gravitation come from Newton era, right? So what has happened now is in 1960, we have unified electroweak theory, but after that, many physicists has tried to combine this strong interaction with the unified electroweak. That is called the grand unification theory. And so grand unification theory does not yet involve the gravitation, and string theory was developed to involve grand unification as well as gravitation in there, and that's we call it theory of everything. But we have so far no evidence of any of these things is correct. Even grand unification has no really evidence that this theory is actually correct direction. So today's so-called standard model of particle physics is an amalgam of unified electroweak theory plus QCD. It's not a truly unified theory, but it is a theory put together into a theory. On the other hand, that this standard model is extremely successful, that essentially everything we see in the particle physics is described by a standard model, except neutrinos that I will talk about today. So to realize the Einstein dream of these unification theories, what we need the breakthrough experiment. The physics is based on experiment. You can't just have a theory, mathematical description. It should be supported by experiment. So we need things like proton decay, SUSY particle discovery, extra dimensions and such. Okay, so here is the building blocks of universe. You may have seen some of these things a lot. So I'm going to just emphasize. We have quarks and leptons in a matter field, and we have 4 forces. As I already said, this electroweak is unified, and the gravitation is still far away from unification from these forces. Each particles has antiparticles. And peculiar thing about neutrinos is that neutrinos only matter field particles that is neutral. All other particles has charge, electric charge, but neutrino has no charge, so they're neutral. So this peculiarity of neutrino makes them to be only matter field particles that can be so-called Majorana particle. So I want to introduce it to you, some of the students who does not know about it. So Majorana particle's definition is that particle, it's its own antiparticle. Obviously, if you have particle as a charge, for example, electron, if you make it an antiparticle, it becomes E plus, then E plus and E minus is different, so it cannot be its own antiparticle. But neutrino, because it doesn't have electric charge, it can be its own antiparticle. And of course, in there, Higgs particle was the foundation of giving matter mass to these particles. And then that was the holy grail of standard model was discovered in 2012 in LHC. So let's talk about the Dirac and Majorana neutrinos. In standard model, neutrino is a Dirac particle, and Dirac particle has neutrino flavor, and then it has left-handedness and right-handedness. So left-handedness is the helicity, this rotation, spin of the neutrino is opposite of direction of motion, that is left-handed. Now, if you have mass, if neutrino has, standard model assumes neutrino has no mass, but let's assume neutrino has mass. Then, because neutrino by definition cannot be going faster than the speed of light, it goes slower than the speed of light. You can find a frame, it goes faster than the speed of light, then you can reverse the direction of neutrino, right? Then you can make a left-handed neutrino by doing Lorentz boost. You can make it right-handed neutrino. That's only possible when neutrino has a mass. Then you do a CPT, left-handed neutrino to CPT. Then particle becomes antiparticle, and the left-handed becomes right-handed, and that's you have an anti-neutrino right-handed. And you can also do a CPT of right-handed neutrino, then it becomes neutrino left-hand, anti-neutrino left-handed. So you end up with the Dirac particles have 4 components, 4 distinctive components. But let's say neutrino is a Majorana neutrino, it's its own antiparticle. Then if you do a Lorentz boost, because it becomes left-handed becomes right-handed, and if you do CPT of left-handed neutrino, it becomes right-handed neutrino, but anti-neutrino and neutrino is the same, so there's only 2 components. So that's the it's very fundamental importance in neutrino for Dirac neutrinos and anti-neutrinos. Of course, as I say, in a standard model, neutrino mass is assumed to be 0. Then this Lorentz boost is not possible. So even for Dirac neutrinos, left-handed neutrino turns into CPT, right-handed anti-neutrino, 2 components only, and then Majorana stays same. Okay. So in the case of neutrino mass is 0, you cannot distinguish between Dirac neutrino and the Majorana neutrino. Another way of saying is the helicity. In the case of neutrino mass is 0 in a standard model, helicity is a good quantum number, meaning once helicity is defined, it will stay as it is forever. So the reason some of you may have heard about neutrino brings a new physics, one of the reasons is that when you write down neutrino mass, you can write down Dirac term, but then because it is neutral, you can also write down Majorana term. We are not forbidden to write that term down because there's no symmetry for forbidding it. That is what drives us new portal to new physics. This is why people believe when neutrino oscillation was made, it is the only Biana-Sara model experimental hint for new physics. So this is my special photo given by Maurice Goldhaber to me personally. This is Maurice Goldhaber, this is Pauli. And I don't have time to explain all of this, what these people has done, great things. But this was a Brookhaven National Lab in 1958. Maurice is a person who devised the experiment in 20 minutes. Is incredibly clever person to measure the neutrino helicity, which I talked about earlier. So this is the experimental setup. He did in 1956. And then Pauli is the person who conjectured the existence of neutrino in 1930s. So Maurice staged this photo shot. So he said, Maurice said to Pauli, "Mr. Radioactivity, I think protons decay." Maurice is also the first person who ever thought about experimentalist protons decay. And he did an experiment that set the limits. And Pauli said, "You cannot be serious. You must be more desperate than I was." And then he said, "I proved that neutrinos are left-handed as well." And he said, "I heard that. Truly amazing. I used to say, I don't believe God is left-hander." This is a photo of Maurice Goldhaber with me in front of my house around 2002. It was raining. We didn't have umbrella, so I gave him my daughter's umbrella. And he was, and it's interesting that he was wearing same kind of coat. We were happy. Okay, so this gives you like literally 1 minute history of how neutrino detectors were built. Original neutrino detectors were actually built searching for proton decay. And as I said, Maurice Goldhaber was the first one who thought about proton decay. But then theorists, to 1970s, Jogesh Pari and Salam came with the first idea of so-called the G224 group theory. From the unification theory, they found that protons decay in that theory. And the Salam didn't believe that in the beginning, but he thought about it, that's it, publish it. So that started that. And then George I. Glaser showed up for SU5 unification theory. They predicted more precisely how much of what is the proton lifetime is and the branching ratio. And so that paper has driven people, experimentalists, go build underground detectors to look for proton decay. You need to go underground because if you stay above ground, there's a lot of muons coming from cosmic rays. It kills your detector, so you have to go underground. And then, even though you go underground looking for proton decay, it turns out neutrinos penetrate everything. So neutrino became a sort of background to underground proton decay searches. But after building all these magnificent detectors, finally, Super Kamiokande, which you will hear about soon, that we didn't discover proton decay, but it gave us great detector to study neutrinos. So all of this neutrino studies actually originate from proton decay search. Actually, this Super Kamiokande NDE, Super Kamiokande NDE, stand for Nuclear Decay Experiment. Okay. All right. So with that detector, 1998, I was fortunate to be a member of this Super Kamiokande experiment when we discovered neutrino oscillation. This is Gajita, who got Nobel Prize in 2015, and then giving young Gajita was giving this talk. I don't have time to describe all of these plots. Most important thing is this particular plot where you're looking at muon-like events created by muon neutrinos coming from the top, that is here, axis. This is from the top. This is muon neutrinos coming from the bottom. And you can see neutrinos coming from the top is here. The coming from the bottom is a factor of 2 smaller. So what this particular plot showed is that neutrinos coming from the top didn't have the time to oscillate, but neutrinos coming through the Earth has time to oscillate, and it turned into something else. So muon neutrinos became electron neutrino, tau neutrino. Later we know that it became tau neutrino. So this plot is giving the evidence or discovery of neutrino oscillation. This one shows many different possible other data samples showing all consistent neutrino oscillation feature in the sine squared 2 theta and then delta m square plane. This paper will be published, superconducting oscillation paper, evidence for oscillation of atmospheric neutrinos, has now, last night I checked, it has about 9,000 citations. Okay, so this is a highly impactful detective paper. And then, as I said earlier, neutrino oscillation is the only phenomena beyond the standard model observed in laboratory venue today. Okay, so I don't know how many of you know Hsien Yang. Hsien Yang was a professor at Stony Brook University for 30 years. He is, in my mind, after World War II, our generation Einstein. He received a Nobel Prize for parity violation. And then he also developed the Yang-Mills theory. Yang-Mills theory is essentially the foundation of all modern theories. And then he also developed the Yang-Baxter theory. And then he also wrote a paper in 1956 on the statistical mechanics that's like Bible in that field. So I had a pleasure to knowing him in around 1997 when we start taking data in the superconductor. I met him at the parking lot. And I said to him, and I called him Frank. Frank, it looks like neutrinos has a mass. And then Frank told me, that cannot be. No mass, having zero mass neutrino, like photon, is so beautiful for the theory. So he used the word beautiful. And so he thinks that neutrino should not have a mass. But then 1998, after superconductor announcement, I met him again at a parking lot. I said, hi. So and then he told me, I guess you're right. Nature is mysterious in some ways, many ways. And then I visited him in 2016 in Tsinghua University in China. And then he told me, on neutrinos, even the smartest person I know, he said, on neutrinos, my intuition failed me. Okay. So this is in his house. On neutrinos, my intuition failed me. Oh, sorry, I went too fast. Okay. So it was nice to talk to him. Okay, after 1998 neutrino revolution, what I call, that triggered many experiments in neutrino physics field. So this is what it looked like. This is not a full list. It is a selected list, especially emphasizing neutrino oscillation experiment. I removed the double beta decay experiment, direct neutrino mass experiment. So these are, you can see the explosion of experiment built after that superconductor discovery of neutrino oscillation. Some of that I will talk about it. So now I'm going to get into grand physics topics we have after that neutrino oscillation revolution. First thing is that we need an experimental input to understanding matter-antimatter asymmetry in the universe. Is this a leptogenesis, a new paradigm? Measurement of CP violation in the lepton sector? Clear theoretical connection between low energy CP violation to high energy CP violation? I will talk about this a little bit more. Is a non-zero neutrino mass and evidence for granulification? CISO mechanism is at work? Then if so, then proton should decay. Measurement of absolute neutrino mass, direct measurement and cosmological construct. I don't have time to talk about this. And then determining Dirac or Majorana nature of neutrino, which I talked about it. This the only way you can do that is neutrino's double beta decay experiment. And then detection or study of astrophysical physical neutrinos, identifying point sources of astrophysical neutrinos, study of ultra high energy acceleration mechanism, detection of neutrinos from core collapse supernova, galactic supernova, detailed study of supernova mechanism, detection of diffuse supernova neutrino background, detection of cosmic neutrino background. Now, detection of diffuse supernova neutrino background is from the beginning of Big Bang. There has been many supernovas went out, and this supernova generated neutrinos all over the place in the universe. So that is floating around right now here. So we would like to detect that. Another thing is that after Big Bang, after 1 second later, there was a huge amount of neutrino were generated. We call that a cosmic background neutrinos. Those are actually non-relativistic. These neutrinos are actually crawl around. They're about, if you stick fingers out again, 1 centimeter cube, there are about 300 these neutrinos going around. And then I don't have time to, that is, if you can devise an experiment to detect those, you will get Nobel Prize for sure. Okay, you should think about that. And then that experiment, I actually thought about it, and I call that as mother of all experiment. It's a very, very difficult experiment. And then, of course, exploration of new physics, precision measurement of neutrino oscillation parameters, test of PMNS. I will talk about this a little bit. And then search for spiral neutrinos, non-stem interactions and such. Can you give me my water? There was right there. Yeah. Look at this equation a little bit. This is so-called PMNS matrix that's described in lepton neutrino mixing. You have mass eigenstates and the flavor eigenstates. These are basically vector bases that can be rotated. That makes a mixing. This is a mixing matrix. That can be written down this way: 3 components, 2, 3, and then 1, 3, and 1, 2 mixing. So in this scheme, there are 3 mixing angles, and then 1 Cp violating phase. It's called the Dirac Cp phase. Once again, if neutrinos are Majorana, there will be 2 more phases. And the only way we can measure this Dirac Cp phase is through neutrino oscillation experiment. We cannot measure that for Majorana phases. We cannot do that with a neutrino oscillation experiment. So here's a little rather complicated the equation. This is general equation you can write down for n generation of neutrinos, how these neutrinos can oscillate. This is a neutrino oscillation in vacuum. So if you write down for 3 generations, new E appearance, from the new mu beam to new E appearance, and that has these leading term, that's a theta 2,3 here and theta 1,3. So it is sensitive to theta 2,3 octant, and then it is sensitive to theta 1,3 value itself. In the next leading term has a Cp violation term, is a sine theta 1,3, 1,2, and 1,3, and 2,3, and then sine delta. The sine delta is the one makes the Cp violation. And interestingly, any of this term could be 0, sine theta 1,3 or 1,2 or 2,3. But nature has somehow given us all of those values to be positive, and that means we can actually measure Cp violation. Now, reactor experiment that looks for anti-electron neutrino disappearance, if you write the formula, that disappearance does not contain any Cp delta. That means they cannot measure Cp violation. They will measure purely theta 1,3. So this complementarity gives us this neutrino oscillation experiment, the accelerator-based neutrino oscillation, able to measure Cp delta aided by reactor measurement on precision measurement on theta 1,3. This is even more complicated. Now, neutrinos, when it's generated, go through the Earth. It's not going in the vacuum. It goes through the matter. So you have to take account of what happens with the interaction with the matter. And I already talked about these 2 points. If you think about here, these all terms contain so-called this x term and delta m square 2,1, 3,1. That this changes sign when we change the neutrinos to anti-neutrino, and that by comparing between neutrino interaction oscillation compared to anti-neutrino oscillation, we can actually measure the so-called mass ordering through matter effect. I will talk about that a little bit more in this slide here. So this is a very important thing to really understand. This is a little bit more expert thing. Now, when neutrino has 3 different flavors, electron, muon, and tau. When they go through the Earth, there are electrons. When it meets, you can have neutral current exchange, and you can have this interaction. But only electron neutrino can have charge current interaction through this diagram. Muon neutrino and tau neutrino or positive anti-electron neutrino cannot have this diagram. That makes the difference between electron neutrino propagation compared to anti-electron neutrino propagation. That generates so-called CP asymmetry. So without having actually CP delta, even though there's no CP violation in delta equals 0, because of matter effect, you can actually generate a CP asymmetry. So that is plotted here as a baseline of distance on the Earth. This red line and these straight lines are the vacuum CP violation coming from CP delta. So maximum about 27% when CP delta is minus 90 degrees, that's minus pi over 2. But as neutrinos travel through the Earth, because of this effect, you can generate the CP asymmetry because of matter effect. So, for example, T2K is 290 kilometers away. June is 1,300 kilometers away. T2K's vacuum CP asymmetry coming from CP violation is bigger than matter effect created the CP asymmetry, which is here. For Dune, the matter effect generated CP asymmetry is actually much larger than other vacuum CP delta generated CP asymmetry. This is reasons why, I will talk about that later a little bit, that Dune experiment can discover mass ordering very quickly because of this effect here. Okay, so the summary here is that this tangling CP asymmetry created by matter effect and delta CP is critical for long baseline neutrino oscillation experiment. Okay, so with this background, now you can see neutrino can oscillate in many ways. There are 3 flavors of neutrinos, and neutrino and anti-neutrino. Muon neutrino can oscillate to mu tau, and then muon neutrino can oscillate to nu e, and anti-muon neutrino oscillation, electron neutrino oscillation that's coming from solar neutrinos, and then anti-electron neutrino, that is a reactor experiment, and all of these things happens. And then that has been all measured. Now, if you look at 2023 particle data group, summary of this, and all of these things are measured, okay? One thing which we note, which, here, is measuring theta 2-3, even though theta is the first one we measured with the Emerson neutrino in a super Kamikaze, but it has still the largest error. So because error is very large, we still don't know whether theta 2-3 mixing is maximal, that will be 45 degree, or greater than 45 degree, or less than 45 degree. If the theta 2-3 is exactly 45 degree, which means somehow nature has chosen maximum mixing between the neutrino flavors, this may mean some sort of profound symmetry in the nature. So determining this will be very important. Another thing which is not known yet is so-called mass ordering. Neutrino has 3 mass eigenstates, nu1, nu2, nu3. We know nu2 is greater than nu1, but we don't know whether nu3 is greater than nu1 or less than nu1. So when nu3 is greater than nu1, we call it normal ordering. When nu3 is smaller than nu1, we call it inverted ordering. So this has not been determined. We need to determine these things. This information is critical for neutrinoless double beta decay experiment. And then finally, the unknown is the CP delta, which is still not measured. And so if their CP delta is non-zero, it will be CP violation in lepton sector. I just wrote down here 2018, how much progress is made from 2018 to 2023. One peculiar observation we have is that if you write down the neutrino mixing matrix, PMNS, compared to CKM matrix, where there are particle physicists here who are working on lab experiment and such, the LHC experiment. If you look at CKM matrix, it's mostly diagonal, and off-diagonal element is very small. But if you look at PMS matrix, that off-diagonal elements are very large. They don't look similar, okay? In the early days, 1996, 97, when I was talking to Frank Wilczek, I asked Frank Wilczek, what do you think about mixing angle for solar neutrinos? He said it should be really small, because to make the unification, that mixing angle of the lepton side should be similar to lepton mixing angle of quark side. But of course, he turned out to be not correct. So this is one of the puzzle that CK matrix is very different than a PMNS in terms of looks. So some of the theorists are working on this thing. And another peculiarity is if you write down mass of a particle, all the quarks live in MeV to GeV to hundreds of GeV. But neutrino, as far as we know, from neutrino oscillations, we know one of them has to be at least 0.05 electron volt. From the present lab limit Catherine, that the mass has to be 0.8 eV. Okay, we have that limit. Also from cosmology, we sort of know now it is 0.09 electron volt. So it is narrowing down somewhere here. If so, if you look compared to quarks, the difference between electron mass to neutrino mass is 10 to the 7 orders of the magnitude difference. So how that can, if they are all coming from same origin of mass, for example, these things are mass is all given by Higgs mechanism, but this doesn't look like it's given by the Higgs mechanism. So we think somehow it's coming from something else. And we introduce something called the CISO mechanism, like SO10 granification theory. In there, neutrino mass is defined by Dirac mass square divided by some very high energy mass scale. That could be 10 to 14 GeV. So if that is the case, if you think about from the Big Bang, there's inflation, and then this is very, very high energy status. And then you can think about this is present day. There's accelerators probing in this area of energy. Neutrino, through the second mechanism and proton decay with a granification scale, is actually reprobing the energy highest to 10 to the 16 to 10 to the 14 GeV, which cannot be probed by accelerator-based experiment. I would like to now change a little bit differently about something I really like. It happened actually 2 years ago. This is looking at neutrinos coming from our own galaxy, Milky Way. So ice cube detector, which is in Antarctica, is array of photon PMTs. And they've been looking at a galactic plane. This is galactic plane. This is a longitude, and that's a latitude. This is the optical view. And then if you look at the gamma rays, high energy gamma rays, most of them most likely coming from pi zeros, and this is what we see. From that observation, you can have the prediction of pi zero population in our galaxy. And then if you have pi zeros, then you need to have also pi plus and pi minuses. Then pi plus, pi minus will generate neutrinos. So this is a predicted neutrino population in our own galaxy. If you look at this circle here, is that if ice cube sees these neutrinos coming from our own galaxy, and that will be the resolution of that. Using new technology of machine learning And they were able to use the cascade event. This is actually basically showering event. They were able to overcome 10 to the 8 to 1 background to signal ratio. And they were able to have 20 times more selected events, up to 2 times a better angular resolution using this new machine learning application. And they were able to see these made observations. So these are neutrinos coming from our own galaxy. This is amazing. I found this is a very beautiful. And then it remind me of, this is like their observation is a 4.5 sigma level of significance. In the Super Kamiokande, we can see neutrinos coming from the sun. So we can actually image sun's image underground by tracing back to a neutrino direction. This is the neutrino image seen by Super Kamiokande underground. So now 1 pixel here is actually size of sun. So the resolution is not that great, but this is very analogous to this. This is a galactic image seen by neutrinos. This is a sun image seen by neutrinos by Super Kamiokande. Okay, so then we have a result on the theta 1.3 and sine squared m2 measurement. The most important thing here is that diabe. Diabe dominates sine squared theta 1.3 measurement. And one thing I would like to note here is that if you look at the error, what they have here, this error is actually 2.8%, is better than their projected error 10 years ago, which was 0.003, which was about 4%. So they are doing actually much better than what they said. I would like to say there are some other measurement, but which is not that important. I will make some comment about this, especially for young students. Generally, when we design experiment, people like me, I'll think about what is the goal of science, and then you design an experiment and you run a Monte Carlo, you predict the sensitivity, because you need to know the sensitivity to make a proposal, and then convince other people join you. But when you do that, you do not have all the technology and things you can have after 10, 20 years later. So what happens is that typically future proposed experiment will do better than expected sensitivities estimated in their proposal stage. T2K has far surpassed original systematic error goals. We set at 10%, but with half of the approved POT, we already surpassed that. Diabe does much better, IceCube does much better, and many other experiments. This happens because improved external input from other experiments, improved theoretical understanding and modeling, and better analysis technique and mathematical computing tools. As you know, and also younger generation is smarter than older generation. And then we have a machine learning and an AI tools you can use, which we didn't have 10, 20 years ago. And then better computing. Some years ago, we were not able to run Monte Carlo, sophisticated Monte Carlos at the time. Now, because of abundance of computing power, you can do so. So here's a result on theta 2.3 and theta times 2 square. This is actually new result from NOVA experiment. And this one summarized, there are many different experiments. This is Super Kamiokande, that's an IceCube. This is an IceCube, that's in a T2K. But all sort of goes into the same direction. This thick line is current NOVA value. This line here is a maximum mixing. So NOVA best point is here. Particle data group best point is there. So it's a little bit off the maximum mixing. However, one thing I would like to note to everyone is that maximum mixing in a maximal oscillation are different. Maximum oscillation, because of this formula here, is influenced by sine square 2.3 as well as this term here. Okay, so actually for T2K, if you calculate, I did this calculation, maximal mixing happens, maximal oscillation happens 45.6 degree theta 2.3. Maximum mixing happens exactly 45 degree, and they are not the same. So distinguishing these two will be very difficult because it's somewhere here. So actually this measurement, whether theta 23 is in upper octant or theta 23 is in the lower octant, or theta 23 is different from maximal oscillation point, will be very complicated. It's a very tough measurement for us to make. So now let me move to quest for CP violation in the lepton sector. So going back to Big Bang, in the beginning of Big Bang, it was at such a high temperature, there's no reason to believe that at T equals 0, there is a baryon asymmetry. So namely, number of antiparticles should be same as the number of particles. There should be equilibrium. But as we know, today, we only see matters all around, including particle, okay? So everything we see is matter. There's no antimatter existing. So what happened to all these antimatters? So that was a big issue. So Sakharov made this so-called 3 conjectures. To have this happen from the beginning of the Big Bang to now, there has to be at least one baryon number violating process, so-called spluttering process, or proton decay, or a C or a CP violation, and then interaction outside the thermal equilibrium. And these are the conditions. This made observation of CP violation in the quark sector are not enough to explain the large asymmetry. So the large asymmetry we see, we have actually discovered CP violation in the quark sector, but that is too small to explain these things. So this led us to believe something called the leptogenesis. In leptogenesis, we believe there's a very beginning of Big Bang, very heavy cousin of neutrino. It has mass of something like 10 to the 14 GeV, but it's neutral because it's cousin. It can be its own Majorana particle, its own antiparticle, and it decays to neutrino and a Higgs or anti-neutrino and a Higgs. If CP violation exists at the time, then it can decay to a little bit more to neutrino than anti-neutrino. That creates matter-antimatter imbalance. To turn that lepton side of asymmetry into baryon side, you need to have so-called a spluttering process where this fluctuation in a vacuum will make leptons turn into the baryons. So all of these things combined can make actually a current matter-dominated universe, and that is the main key point of leptogenesis. We don't know whether this is true or not, but we would like to find out. And to make that work, first we have to figure out CP violation actually occurs in the lepton sector. That's why we are doing all this accelerator-based experiment to establish CP violation. So all this accelerator-based, the large experiment, future experiment we are doing, current experiment, is looking for muon neutrino generated in an oscillating the tau neutrino, but some part of it, about 5% of them, can oscillate into electron neutrino. So we look at electron neutrino appearance, and then we do the same thing for anti-muon neutrino to anti-electron neutrino. If the rate is not same, of course, excluding the matter effect, then that will discover the CP violation. So that's what we are doing. So 3 experiment is the leading in that X area is called T2K is the leader. So here's the CP angle from 0 degree to minus pi to plus pi. T2K is from current data about the CP delta best value of minus pi over 2 in this area. Nova, for normal ordering, is this blue curve. You don't see clear minimum. Actually, it's kind of spread out. But for inverse ordering, you see clear minimum here. Nova plots different angles, so 0 to 2 pi. So 3 pi over 2 is the same as minus pi over 2. So it's consistent. The T2K minimum for inverse ordering is same as Nova minimum in the inverted ordering. Super Kamiokande has a less sensitive, but it does also see the minimum minus pi over 2 for normal ordering, and then for inverted ordering. So we combine them all together here, put together in one plot. You see the blue is a T2K, and then this is a super K, and then this is nova. They all kind of overlap. There's some tension between T2K and nova. For inverted ordering, they more or less all agree. This is a T2K, this is super K, and then this is nova, and then this is super K. So if you have this experiment measuring the same thing, it's natural to think we should be able to do joint fit. So super Kamiokande and T2K started doing a joint fit, and then T2K and nova started doing joint fit. In fact, this was under when I was a international spokesperson. I pushed for this thing 2016. So it takes a very long time, but the idea is that super K sees a neutrino oscillation baseline to 15 kilometers of 13,000 kilometers with an MS2 neutrinos, broad energy band, and water Cherenkov detector. T2K is tuned at 95 kilometer baseline, excited neutrino, narrow band beam, and then it has a fine-grained near detector and a water Cherenkov far detector. Nova is 810 kilometers, accelerated neutrino, a narrow electron neutrino beam, and the functionally identical near and far detector, and the liquid scintillator detector. So they have very different complementarity nature. By combining it, we can gain better sensitivity. This is one example showing T2K alone is this kind of blue line for normal ordering, and then it doesn't have a lot of sensitivity in here. Super Kamiokande has not much of sensitivity, but when you combine the two, this red line shows we gain a lot of sensitivity in this region. So that's the power of doing joint fit. So full joint fit with a correlated interaction and a detector systematics was done for Super K and the T2K. The first data fit result was released, archived, and accepted for publication in PRL just this month. So this is a very new result. I will show you the plot. And then T2K nova, as I said, joint effort started 2016. There are many differences in analysis method. It was a very difficult process, but paper is now finally in preparation for publication, and result has been already publicized. So this is the first T2K super Kamiokande joint fit result. Here is you see the sine theta 2,3 and delta CP plane. What you're seeing is that this blue is T2K, and then SK is this kind of dotted line. So by combining it, this blue has shifted a little bit towards more maximum mixing. So that's the net result of T2K SK joint fit, but delta CP has remained around minus pi over 2. You can do the same thing expressed in the Yarskov invariant. This is Yarskov invariant value. When this is 0, that means no CP violation. So in this test, all of the things for Yarskov invariance or delta CP equals 0 or pi, so CP conservation, that our sensitivity, right, not sensitivity, our result is about 2 some sigma. It's not yet 3 sigma level. So it takes still, we cannot call it yet evidence of CP violation that will require 3 sigma by convention. Here's the result on first T2K nova joint fit. The line show the red circle shows the T2K, and then this one here is the nova. For normal ordering, this is inverted ordering. By combining this shaded region, dark shade is the new result. You can see the T2K result will push a little bit to the left towards a minus pi. And for conclusion of this is for both mass ordering, both normal and inverted, delta CP pi over 2 lies outside of 3 sigma credible interval. This is a very significant statement. So minus pi over 2 is no longer viable solution for delta CP. For inverted ordering, CP conserving value of delta CP equals 0 or pi lie outside of 3 sigma credible interval. That means that inverted ordering with a CP delta to be CP conserving will not likely the nature choice. So that's a quite significant advancement. Now, this year, NOVA has also doubled their data in terms of neutrino mode. So they released a new result. So this dark blue is the NOVA result, new result with twice of data. And then the light blue is their old one. So you can see the change. You can see the change has, I can actually subtract this. I asked the question whether if they look at only new data, their new data disagrees with T2K a little bit more or not. They didn't make the public statement. But by substringing in my head, I can see that actually their new data is more agreeing with the T2K measurement here. So they are becoming more and more in the section here for the best fit value. For inverse ordering, it's clear that everybody agrees that inverse the minus pi over 2, the only remaining errors here, pi over 2 is completely excluded. Right? And then NOVA is planning to double anti-neutrino data set for the next analysis. So NOVA is projected the sensitivity for at the end, they're gonna ending their data taking on 2026. And if delta CP is minus pi over 2, they have some chance of looking at 3 sigma in terms of mass ordering, and the delta CP, they don't have much sensitivity in delta CP, but in terms of mass ordering, they can go to almost 4 sigma level. Well, so that they are hoping that at delta CP is actually minus 12 over 2. T2K is sitting here. T2K will end data taking in 2027 if hypercommutator starts at that time. Currently, beam power is greater than 800 kilowatt. This is great. And also we have increased the new Horn current to 320 from 250. And this is generating a lot more data. So in new T2K, this year, if we take 1 year of data, that is equivalent to 5 years of data taking in last 10 years. So this is a huge amount of new statistics. Now, with this increased statistics, we could reach something like 3 sigma level if we are lucky. But to do that, we need to reduce systemic errors. So we devised that ND280 upgrade, here, which is shown here. This is the original T2K near detector, which has a magnetic field and it has a fine-grained detector inside. We have removed this part detector, and then we're keeping this part of detector same. We'll remove that detector, and then we'll put in a new, very sexy detector called a Super FGD, which is made out of 1 centimeter cube scintillator, optically isolated one, 2 million of them, and then has a 3 wavelength shifting 5 going through and read out by MPPCs. This is essentially pixel-like scintillator detector. That is in the center here, and then we have 2 high-angle TPCs to put it in. With this detector, we can have much better efficiency in terms of all the angles through the all angles. Our old detector has a deficiency when track is going vertically in terms of making that the track reconstruction. And also when you have short proton tracks, we were not able to reconstruct that easily. The threshold is very high, 400 to 500. With the new ND280 upgrade, we are lowering that threshold to 300. Most important things, which is that I love about this detector, for the first time in particle physics history, this detector is capable to detect the neutrons coming from neutrino interaction. And then you can measure by neutron interactions, you can measure distance from the vertex to the neutron interaction. We can capture neutron kinetic energy event by event. So this is the first time. Neutron is usually considered as a missing energy. Now we will measure that neutron and put it in the event reconstruction and then eliminate a lot of systemic errors coming from that neutron. So this is some of the beautiful event plots. This is the ND280 upgrade Super FGD here and the high angle TPC. You can see that very small track here. That's most likely a proton, and the muon goes through the entire detector and with a magnetic field bending. And then this one is a multiplicity, high multiplicity event interaction with lighting up all detectors. Super Kamiokande is now Super Kamiokande gadolinium phase. Let me just make this one very simply. This is a well-known inverse beta decay anti-electron neutrino coming from supernova will interact inverse beta decay with a proton, generate a positron, and then you have neutron capture, creating this classical signature. The main thing what they are looking for is that with this, you can look for diffuse supernova neutrino background, mainly all the neutrinos coming from supernova explosions. They have energy of around 5 MeV to about 15 MeV. And you can look for these neutrinos. And then what they think is that these are the predictions. There are many different predicted models. For some years of data taking, their sensitivity goes here. So about half of a model, if it's correct, they will discover this supernova, the neutrino background. So looking forward, 1999, I established something called NNN, Next Generation Nucleon Decay Neutrino Detector Workshop Series. The first one was held at Stony Brook. This is book. These are the proceedings. These are the papers published in that. This is a photo from there. What I'd like to pay attention to is that this person, Shiozawa, has at the time, 1999, studied 1 megaton Volchenkov detector for future proton decay search. And he is now Hyperkamiokande spokesperson. So think about it. It's like more than 25 years ago. So you could be writing such paper, and then you could be spokesperson of that future experiment. And then another paper had a liquid argon detector, and Angel Rubia, he was a former Dune co-spokesperson. So you need to think really far ahead when you are young. In these days, because of detectors and things, takes time, money, and the collaboration. So it is very important to think about these things very early ahead. And then this NNN series is held every year. 2019, 5 years ago, we came to Latin America for the first time in Medellin. And this is an NNN workshop at that time. Some of you can identify yourself. And then, but this year, we went to Rio, Brazil. So NNN series workshop, and then the second lot. Now, Latin America in the rotation of NNN series workshops. So let me quickly go through next generation large multi-purpose neutrino experiment. First is Juno. Juno is being built in China. Construction is almost finished. And what they are looking for is they are looking for neutrino and the anti-neutrino oscillation from reactor for this large oscillation, which measures theta 1,2, but they are looking at wiggle in this thing. And this difference in wiggle can measure mass ordering. This is a very different experiment. And then to do these things, you have to control energy scale, energy resolution. But anyway, they are expected to start filling phase in December of 2024, basically this month. They think that they will determine mass ordering with the reactor neutrinos 3 sigma in 6 years. So it's a tough experiment. They have potential to discover diffuse supernova neutrino background. And then they can see neutrino burst at 10 kiloparsec. 10 kiloparsec is beyond the center of our galaxy. And then other measurements, other neutrino oscillation parameter measurement. I visited there in February, so you can see that it's true. Their construction is almost finished. Hyperkamiokande is built in an essentially similar site in a Super Kamiokande. It is 70 meters diameter, 7 meters tall. This is super K is 40 meters and 40 meters, so much larger, about 4 or 5 times larger than super K. Application will start in 2027, and it will use the same beam, generate the super JPOC, east coast of Japan, send it to right now it's super Kamikande, but it will go to hyper Kamikande as well. Primary goal of physics is CP sensitivity. For about 10 years, they will be able to discover CP violation in 5 sigma. And then this is one of my favorite things. If neutrino coming from in our galaxy, there are huge number. Super Kamikande can see about 9,000, I believe, for hyper K about 50,000 neutrinos in 10 seconds. Then you can see in time, if after collapse of supernova, neutron stars formed, then it will look like this. Black holes formed, it goes like this, flux, and suddenly truncates because black hole sucks in everything. And so this will be live observation of black hole by the hyper Kamikande. This will be fantastic. And then they can also search for proton decay to e pi 0 to 35 years. Hyper Kamikande construction is almost finished. This is the status here you can see. Cameron construction will be completed in December 2024, this month. June is where I'm working on some of the Colombian members here. It has 4 far detectors and the near detector, capable near detector complex that actually moves around. And then phase 1 has 2 far detector module and a 1.2 megawatt of beam. Phase 2 has all 4 far detector module of 2 megawatt of beam. Non-beam physics operation will start 2030. As I said earlier, this plot is most important thing. In June because of large distance, 1,300 kilometers, we can discover mass ordering. If IPSC has all CP phase in probably 2-3 years of running. And then the CP violation is more challenging, but for 340 kilotons of exposure, kiloton megawatt exposure, we should be able to discover 5 sigma in about 10 years or so. Good chunk of the CP delta. And then for core-coalesced neutrinos coming from the supernova, June has a very specific thing. All of the World-Chenkov detectors measures nu E bar, anti-electron neutrino, but June can look at the electron neutrino coming from neutralization process of supernova in a very, very early time of the supernova. So you can see that this peak of electron neutrino, that will be a fascinating thing to detect for us to really understand supernova mechanism. Here is the current status of June. So here is the horizontal drift FD1. Not current status, this is what it looks like when it's all built. The FD2 here, this side. And then FD2 is so-called the vertical drift. FD1 is a horizontal drift. Originally planned, this one, horizontal drift will build the first, operate start. But we have decided that FD2 will be built first, and it will operate first. And then it will be built in sequence. So here's the June far detector cabin completion. You can see all of these things done. We had the ribbon cutting ceremony. So data taking, as I say, start in early 2020. Muchos colombianos están haciendo contribuciones significativas a June. Okay, that's important that Colombians are making that. Now, how much time I have? I can skip some of these ones. This is the planning and proposal stage experiment. KNO is the large version of the even bigger than Hyper Kamikande they are dreaming about in South Korea. They were doing R&D and a planning stage, but I visited Korea a few months ago. It seems like this activity is stalled because the government is thinking more participating outside international collaboration. THEA is proposed based on so-called water-based scintillator detector. So in this detector, you will have water Chenkov signal as well as a scintillation signal. So that gives you a benefit of able to reconstruct events much more precisely, reduce background. This detector is proposed as a far detector force module of the dune or standalone detector itself. And I'm not going to say much about this thing. There's a Europeans building spallation source in Sweden, and they are trying to use that neutrinos coming from spallation source to the long baseline experiment. This is just a planning stage. And then IceCube has a proposal. Current IceCube is here, and they want to make a much bigger array, and then put in a radio array on top of the even much more bigger. This is fantastic. If you do that, you will see a lot more of the point sources coming from astrophysical sources. But then going smaller, they're also trying to make it in the middle, some sections more dense. They call it IceCube upgrade. If you do that, there will be a 1 GeV level of threshold. And then there are many other underwater telescopes are being built. So I'm going to finish up. There's a unitarity violation, which I talked about earlier, can be done. But let me just conclude that you can see this slide. I will post this thing. It's very hard to test unitarity, lepton unitarity in the mixing sector, lepton sector. And then we can build things called a Newstorm or Neutrino Factory. And Neutrino Factory shares a lot of infrastructure with the muon collider. This can fit into Fermilab. So this is muon collider being seriously discussed in the Fermilab. And so this could be part of our future direction. However, the cost is very, very, very high. It's very difficult to build such experiment and accelerator without strong physics motivation. So we need a theorist to think harder to give us good theoretical motivation. Another thing is that if we continue proton decay, that started the whole neutrino science, you need to go 10 to the 36 or 37. The only way I can see is making IceCube turning into a proton decay search experiment. So I call it IceCube PDK or IceCube NDK. That's a dream. So let me conclude. Since 1998 neutrino revolution, we made a remarkable progress in understanding the neutrino properties and its implications on the understanding of the universe. We are at an unprecedented time in neutrino physics. The next generation experiment, Juno, Hypergate, Dune, are coming soon. The combined cost of Juno, Hypergate, Dune is $5 billion. We spend a lot of money. Both expected and unexpected discoveries are highly anticipated. Exciting times is ahead. Maybe second golden period of neutrino physics is coming, 2028 to 2043. First was 1998 to 2013. And in order to ensure continuing a success, the third golden periods, we need to start planning now. Young people have to think about this. Next generation experiment will cost even more and take longer time to realize. As I said, IceCube, NDE, or Neutrino Factory, or muon collider. Strong physics modification is needed, challenge to the theory community. Continued progress in detector, liquid argon, TPC, and et cetera technologies, absolutely essential. So I usually show this Mount Everest as a quest for CFE violation. We are making progress, and we know how to get there. But what I want to show you this is the highest peak in our planet, Olympus Mons. This is Mount Everest, so it's much higher than that. We need to go there for proton decay, non-unitarity, sterile neutrinos, non-sterile interaction, unknown surprises. Okay. This one was Maurice Goldhaber was 90 years old. He said this. One of my favorite quotes. I say, a proton may live forever, but it gives us great neutrino detectors. Okay, so I'm sorry I'm taking a long time. I have to say this. I want to make special congratulations to David Martinez, who's here. He received 2024 U.S. Department of Energy Early Career Award. This is a very prestigious award, as a young assistant professor, if you get this, your life is set. You can actually retire. You don't have to do anything. You get tenure. So he actually got tenure this year. He's an associate professor of physics of department in South Dakota School of Mines. He was born in Pasto, went to University of Nariño. He's a graduate from here, and then went to Brazil to get PhD, and he's now in South Dakota. Okay, so this is, muchas gracias, me encanta Colombia. Los compañeros son gente fantástica. You remember Mr. Pollo? This photo is taken in Mr. Pollo, and then other photos. This is my house and living room. I have that Colombian flag. Okay? Thank you.
Okay. Do you hear me?
Yeah.
I have a question related with Ice Cube because you talk a bit at the final of the presentation about it. I'm interested in know what is the new knowledge that we can get with the improves of the Ice Cube detector, because you say that Ice Cube could be larger with more detectors. I suppose it could increase the detection of the high energy, ultra high energy particles.
Yes. So Ice Cube is right now detecting. What we like to do is original goal of Ice Cube is that finding point source, an astrophysical point source where the neutrinos are coming from. But the detector is right now not large enough, statistically limited. Okay, so by building a large detector, you can have much higher statistics that they should be able to discover point sources. So that's what new things we will learn. Yeah, that's clear goal. And then I'm big supporter of that. Even though I have nothing to do with Ice Cube collaboration, but I'm fan of Ice Cube.
The last question.
It's okay. It's Colombia, no?
Thanks, Professor Chang Kee, for this very nice talk, very for the summary of the Neutrino Experiments. So I would like to know if Hyper-K can reconstruct the supernova explosion, so the site, the location of the supernova. Is possible to reconstruct at some point the location?
Point? Yes. So
In order to combine, for example,
I wanted to give you an overview, so I didn't go to any of details. One thing was Super Kamikande and Hyper-K can do. You can look for electron neutrino comes and scatter elastically. Okay, so then neutrino comes in, kicks electron goes this way. That is basically the same thing as solar neutrino observation. Solar neutrino is observed by electron direction by going backward. Okay, same way, supernova neutrinos can be traced back for this particular elastic scattering. So those numbers are not that great. For Super Kamikande, it has about 300 such events for galactic supernova, but 300 is enough to point back. Okay, in the Hyper Kamikande, you will have a lot more. You will have about over 1,000, probably 2,000, around 2,000 events. So you can point back, yes.
And the uncertainty? The uncertainty?
Oh, I don't know. I mean, depending on the problem is that where the supernova is, distance makes huge differences in the statistics and uncertainty, all of that. Right.
Okay.
Thank you.
I think it's a couple of degrees you can do it.
Additional questions with the speaker at the coffee break. Yes, the Professor Carlos has additional.
Wait,